you hear me? Can everybody hear me? Okay, perfect. So what we would like to do today is to practice with problems on capacitors. And so then what I will do is I'm going to ask you, like in the middle of the class, to do a very fast exercise with respect to things, just as a review. We'll cover it here and then I will ask you to do it, just to make sure, because a lot of these problems that we will solve from now on will depend on the things that we have seen. A lot of problems of capacitance, for example, whether it is from a parallel plate capacitor or from coaxial waveguide capacitor. Usually the ones that you will mostly see in circuits are parallel plate capacitors, all right? And people create them in all different interesting ways. So before we start in this problem, because it's going to be very relevant what we are going to do here, let me remind you, in fact, if I may, go to summary. Okay, this is the summary that I would like you to remember. Okay, so point charge. Let me also ask you here. You have a point charge. You have a one is what we've seen, 1 point charge. So this is like a summary, quick summary of things that we have seen. You have a point charge Q. How does the electric field go away from the charge? In fact, what is the expression for the electric field? First of all, since it's a point charge, we have the spherical coordinate system. All right, so spherical. That's what you need to remember, coordinate system. Usually a spherical coordinate system is as part of R or capital R, lowercase r or capital R, phi, and theta. All right, so here, sometimes you see it like lowercase r, some other times you see it as capital R. Usually with capital R, at least in this class, we indicate the distance from your source, all right? But anyways, you will see it like that. So how does the electric field, first of all, which direction does the electric field have? Spherical have the radial and two, all right? They have the radial direction, spherical has the radial direction, and then has the phi and theta directions. Which is the direction of the electric field in this particular case where you have a point charge? Somebody tell me. If I go at this point, A, what is going to be my direction in the electric field? Radial. That's how we say radial. All right. Since the Q is going to be at the center of my system. Okay. So E is going to have the radial direction. That is the radial direction. Is a bar. How is it going to vary? Approximately, it's going to vary as what? If this is O, if this is R as vector, how it's going to vary? 1 over magnitude of R square, all right? 1 over magnitude of R square. That's how it's going to vary. What is the exact expression? 1 over 4 pi epsilon naught. And then you have Q over, and then you write it like this with unit vector, or you write it like this, if you are to use the vector R there. All right, vector R is this one. Vector R is this one. And that is A sub R. which is the radial direction, all right? So, but you remember it goes as 1 over r squared, the magnitude of r squared. What happens if this Q is distributed over a volume? Let's assume that it distributed uniformly over the volume. This is Q sub S, Q sub V, excuse me, it's volume. And if the total is Q, how much is the field gonna be here at this point? Let's assume that that's the center. O, A. Which direction is the field gonna go? Nobody? Yes. Thank you. The field is gonna be, this is again R. The field is gonna be identical. I mean, that's the one thing you need to remember. The field at that point outside of the charge, of the uniform charge, is gonna be 1 over 4 pi epsilon naught Q, because this is the total Q over magnitude of r squared, and it's gonna have the same unit vector along the radial direction. Remember that? It does not matter whether the sphere is small, big, nothing matters in this case, all right? It does not matter if the sphere is like this or the sphere is bigger. And all of the charge distributes over a bigger spherical area. It does not matter if you are outside of that, you see exactly as if it were all concentrated at the center. Okay? Cylindrical. Now, the charge, first of all, start with a line charge. Okay, line charge. Q sub L over a line, infinite. How does the field vary if I am here? Which direction will the field have? This is a cylindrical system, all right? Let's assume that we have a cylindrical system here. This is the Z direction, okay? And this is a cylindrical system. Usually in cylindrical systems, this we call it rho, all right? Cylindrical system has rho, phi, and Z. Remember that? And phi is the angle. Okay, if I am at this point, this is an infinite cylinder. What is the direction of the electric field? Rho, exactly. So it does not matter where you are. If this is rho, the field is gonna go along the radial direction, which is A sub rho. All right, and the field here is gonna be, let me put the value first. How it's gonna be in the denominator, you remember? Okay, 1 over rho. What happens if instead of a line charge, I have the same charge distribution? Yes. Yes, so, thank you. Yes. So what happens if the same charge, which is a line charge here, it's a line charge, I take it and I distribute it over an area, so it becomes like a cylinder, all right? So my charge now, the Q, the little QL, all right, that it was at the one, I mean, if you look at the cross section, look at the cross section. The cross section here would have been, all right, and the charge would be at the center, like this. And that there would be on that cross section specifically, it would have been Q sub L at that point. What happens if this Q sub L I distribute it over an area uniformly and this area looks like this? Here. I don't change the value, I just distribute it. So instead of a line charge, I have a surface charge practically there, all right? In reality, it's gonna be, overall, it's gonna be a volume charge because obviously, if you look at 3D. But in any case, instead of a dot on the cross section, we open it up. So practically we have an infinite cylinder. So the whole charge thins out, obviously, but covers uniformly one cylinder inside, okay, in cylinder, in the way I have it. How much is gonna be the field now from this cylinder of charge, uniform? Okay, let me also do that, same thing otherwise. Okay, so here. Now, all right, so now this is the charge, it goes extends. How much is the field gonna be there at that point? What do you think? Yes, it will be exactly the same because you are far away and you just see that, but the impact of this even distributed on this rod, if you like, all right? Charge outside, you're gonna see the same. Inside is where things change, as it happened with the sphere, all right? Okay, parallel plate. Let me have now parallel plate here. And on this one, I have a charge distributed evenly. Q sub S, evenly on this. And that is infinite long, infinite along both directions. What do I see here? So this is XYZ system, obviously. Let's assume that this is the Z coordinate, all right? What do I see at this point? What is the value of the field at this point? A. And let's assume that that is at a distance D. Distance D from the ground. How much, what is the direction of the field and how much is the field gonna be, the electric field? What do you think? What is the direction of V? Z, exactly. It is perpendicular to the surface, Z. How much is the value of the field, the magnitude? How does it vary with B? Constant, and it's gonna be Q sub S divided by 2 epsilon naught. Okay. What is gonna happen if I place now a layer on top of this? So see, we say all of these things without looking at equations. That's why I would like you to remember those fundamentals, not too many. We're not gonna remember too many things, but we are gonna have to remember those. So let's assume that I put a dielectric. It does not have charge or anything. The charge is at the bottom. I put a dielectric there. and the dielectric is this one, all right? And then I'm going above the dielectric, above, and what do? I see, I look at, measure the field. Same distribution of charge, just I have a dielectric in front of it. How much the field is gonna be in the new case? Direction and magnitude. What is the direction of the charge gonna be? Same. Same. Okay, let me see. Same. All right, so E is gonna be EZ, AZ. How much is gonna be AZ? EZ, excuse me. How much? What's that?
I have a question.
Yes.
So is the dielectric covering the surface more just like the sides?
The surface, I mean, it's the whole surface. I cannot just do it. The whole thing is infinite with the dielectric infinite, the planar and the dielectric, all right? How much is gonna be, question? How much is gonna be E sub Z? Think physically, forget about equations, just think on the basis of what you know. Think in terms of flux. Flux in reality shows how many field lines, like think of the charges as the source, and the flux shows how like the electric energy direction goes. All right, think of that. All right, think it that way. Get that kind of really, it's not exact, but kind of feeling. All right. So if you have the same charge, you cover it with the dielectric, no losses, nothing, just dielectric. Perfect. And you go above there and you measure the field. What are you going to see? Are you going to see the same field or different? Why? Where's the rest going to go? I mean, if I see a different field, that means my flux, my energy out of the charge is going someplace else. Where is it going to go? It's not lost in the material. We have to preserve energy. So if I see less, where does the rest go? Nowhere. So we see the same. All right? We see the same. That's how you're going to think about that, because if you're not prepared to understand what you're looking for, the equations, if you make one mistake in an equation, you can come out with something crazy. But if you know what to expect, even if you come out with something wrong because you made a mistake somewhere, you know that what it came out is not quite right. Yes. No, the dielectric is not perpendicular. It covers the surface. Yes. Yes. I don't know. I'm not very good in drawing, but it comes like this. All right. It's like a film. Let's assume that your conductor has the charge, and you put a thin dielectric film on top of it. Is this going to change your field? No. If I have an antenna and I'm going to protect it from the elements, I have my antenna. A lot of times, have you seen those large antennas, especially in the military, you guys are, that they are covered with radomes? This white stuff, this huge antenna, especially on military ships or other airplanes and stuff, they have a radome. They want to cover it. They want to protect it from the elements, whether it is, you know, birds for the planes, all right, whether it is something else. Do these radomes change the field that the antennas radiate? No. If they're good dielectrics and they don't have any losses, no. Otherwise, why would we put it there? I mean, people are dying to get these antennas to radiate something really important, and then you're going to put something and lower it? No. So these are the kind of thinking, all right? Because otherwise, you have to ask yourself, if I don't get the same electric field, which means I don't get the same electric energy, where does the rest go? Cannot just evaporate, all right? Is it becoming heat? Like why? I don't have finite conductivity. I don't have dielectric losses. Is it going to the side? Why? What will force now all of a sudden the field to go to the side, the dielectric like this? I mean, if it were to go to the side, it would have gone to the side before, all right? So, any case, these are the things that we have, in fact, reviewed. And I think this is going to be important as we will solve the capacitor problem. So at this moment, I will give you something very simple. Let me just start it. This is the first time I start something here. So I'm going to start a new question. Multiple choice. Okay. And the question says the following. I have a charge, write it down also, I will put it here, distributed on a perfectly conducting sphere. So the charge is distributed on the conducting sphere, okay? And the charge is Q. The sphere has a radius R sub S. R. Let me call it sub S here. Sub S. Okay. What is the direction? How does the field vary? This vary with distance R from the sphere. Okay. Obviously, when R is larger than R sub S. Okay. And then here, as over as. Okay. So I'll put the same. So it's 15 and 15. 15. Okay, and then say here. Okay. Other. And here is question. All right, so sorry, I'll save it. All right. Let me see. Question in class. I have. Okay, so then I will assign it. All right. let's see, it's very a small variation of what we had before. Do you have a laptop? You wanna? Okay. Did everybody have the chance to respond? Is there anybody who needs more time? Okay. Okay. Thank you. Are you ready? Okay. Are you guys done? All of you? Okay. How about you? Okay. So I'm gonna unassign. Pretty good. Most of you responded to the correct thing. Why is that important? So the question was the following. Let me, in fact, do this. The question was the following. If I have now not a point charge, not a dielectric and a charge, but I have a conducting sphere, and a charge Q is distributed equally everywhere, all right, on the conducting sphere, uniformly. And why will it, first of all, I said that I did not even have to say this. Why is that? Because the charges, which are a sum of many, all right, charges, will go, and then if you let them, when we say for example, that we have a total charge of so many nanocoulombs. It means that there is a sum of many infinitesimally small charges. So all of these, like holes, for example, they will feel charges, all of these infinitesimally small particles that they are charged positively, think that way, they will feel repulsive forces. So they will have to balance them. If there is nothing outside, eventually they will balance out in a uniform way, all right? That's the only way to balance. If every small of these positively charged particles, for example, are identical, and the forces in between them are identical, or they will balance out on the surface of the conducting sphere, obviously, because inside they cannot go, uniform. All right, I did not even have to say this, but let's assume that we did. Then I go at this point here. And since it's a sphere, I still take the system, the spherical. So what I see there is exactly the same idea, all right? I will not see a different field. I will see one field that changes as 1 over r squared, and as a matter of fact, identical to what I would have seen if the whole charge was concentrated. That's the other interesting thing, all right? The only way that this is not going to be true if there are other bodies around that are charged, or other charges somewhere around that disturb that kind of distribution and they do other things. But obviously in the case, it's going to be, at least it's going to vary as 1 over this square that you know. So this kind of thinking is important as we go to these problems. And the first problem, in fact, let me see. Okay, so this is a problem I gave to a meter for a class. Now, what it says is the following. You see that, say, oh my God, you know, what is this? I've never seen this before. But when you start layering, and then you go into these questions methodically, let's do the first one only, that says, find the total charge on each of the conductors, 1, 2, and 3. You have 3 conductors, 1, 2, and 3. You have 1 dielectric in one case, you have free space. I mean, you know, in reality, you would have 1 and 2 dielectrics, but here dielectric up here, free space there. The area is the same, like you have 3 identical planar conductors, finite area here. I don't even give W and A and B, for example. I just give the total area, but I give the distances between the conductors and the material, of course. And then I put a battery, 1 battery here, 1 battery there. Okay, that's all. And the other thing I'm asking you is find the total charge on each of the conductors. So first of all, let's think without getting, that's what I said, in these problems, you don't try to write down, say, oh, what am I gonna write down, you know? I don't know what you would write down. I mean, if you start thinking, without having a plan for the solution and a thinking about what do you expect in general, you cannot start writing stuff. But I would say the following, say, okay, you have a battery here. Let me start with these 2. I have a battery. So obviously I have a positive charge here. It comes here. The positive charge, so I will, okay. That's the first thing. Without even equations, up here, you have already solved 90% of the problem. Just with this schematic, because you say the following. I said, okay, I have this battery here, it sends this charge, and this charge, this is an ideal, of course, connection, all right? Usually in reality, you have a true connection there, there will be some unevenness of the charges. But at this point, this is ideal connection. So all of the charges will distribute evenly on the lower part of the surface. Okay, they will go there. All right. Why are they not going to go up front? They go underneath. Because they see another metal there. All right. They don't see anything here. There's nothing there. All right. All of the activity happens here. There are other negative charges here. They don't see anything up here. So the moment the positive charges go there, there are also negative charges going here. And because of the forces, the total charge positive here is going to show us negative charge here, but the value is going to be the same. So if this is Q1, this is up here is going to be minus Q1. All right, that's how they, because all of the, you see the positive charges sit there, all of the electrons, they are going to be attracted and they will try to go as close to them as possible so they will flow on the upper surface. All right, minus Q1 there. I have here another capacitor on the third one, and I'm saying here Q3, but in reality, I know because they are identical, I could give them different values to the two batteries. So if these two batteries have the same value, so here I would say I have Q3, but Q3 is going to be the same with Q1 because the batteries are the same. All right, so if I have Q positive Q1 here, I will have negative Q1 there. Negative Q1 on this side, negative Q1 on this side, and positive Q1 up there. All right. So it is interesting that the center conductor has a lot of negative charges. Why is that possible? Only because of this connection, because it's connected to the ground. If I had given you a different problem where this line would not have been there, but you would have something like this. All right. Had I given you this center conductor could not have this floating negative charge. Where would it get it from? Before we apply the voltages, everything is in equilibrium. All right. So before any voltage is applied, there's no charge here. Where's the negative charge going to come from? Where would be the positive charges? They would leave behind if it were the electrons of the metal. They cannot go to the center. There's nothing at the center of the conductor. So what would happen in this case? See, in this case, this cannot exist. So you will not have any charge there, which is kind of interesting, all right, for a problem like that. So anyways, we are solving these problems there, but in reality, for this one, I wanted to show you there the initial problem and how from the moment then you because here obviously the capacitances now, if the charges are the same, if the charges here and here are the same, all right, in this problem, so you have practically in this problem a voltage VT here and another voltage VT there applied, all right? There is the electric here and there is air here. So the only reason the charges, these Q1 and Q3 will be different is because one has dielectric and the other has free space. And you know why? Because VT is constant. That means that the electric field here and there will be the same. So you will have, we'll do that next time. I'm not going to get you into this moment. The only thing that I would like you to do is to check, in fact, the, I want you to just feel comfortable on how charges go and when they see against each other, and what will be the possibilities on the basis of just fundamental physics of how these charges get distributed. We'll do this problem in detail next time. Because, for example, I'm giving you also this problem here, all right, which is kind of interesting. I said, okay, what happens in this case? If this line is disconnected, or if somehow my line, I could have a conductor like this in my circuits, all right? It could be a common ground here. And I could have a common ground here. And then especially in what we call the system on a chip architecture, where you have multiple layers of silicon, and then you have capacitors at different layers, depending on what they connect with. You may have one, usually in a system on a chip architecture, you have multiple grounds and you have dielectrics in between. The grounds are not infinite, they're finite, but they have to be grounded. What if one of the grounds in this conductor is broken? Or some via holes are not working, or somehow the designer forgot to put a ground in there. Then what happens, which is interesting, is that the charges, all right, there's going to be one charge here, Q1, Q1 here, and Q1 there. But this conductor cannot have negative charge that sustains itself, all right? Cannot do that. So practically, the only thing that you see is in fact how you see it here. You cannot have on this one, all right, a negative charge. In fact, the charge has to sum up to zero at that point. There is no way of having negative charge here. And then if this is zero, this is zero, this is zero, the whole thing. So practically, there are no charges that are excited in this one, in this particular configuration. Which what it shows, also very interesting, is that like that it did not exist, and then you had two conductors that have the same charge, which means they will not work like a capacitor. Will be just two conductors with the same charge, and in fact the field lines will go outside. All right, the field lines between them will be very weak. Okay, so these are the kinds of things. So practically, you would think if you go to the lab and you try to measure, you're not going to see any capacitance there. Capacitance is going to be hugely weak, even if you apply two voltages there, because this one stops the fields, exposes these positive charges, and stop the fields from developing internally. So the fields from these positive charges, the charges will go to the outside of here instead of going to the inside, because they're not going to see anything there. It will go to the outside, and therefore all of the fields will be outside of the capacitor. So you're not going to see any, and that capacitance is going to be teeny. All right, because all of the field lines will go everywhere. So that's are the kinds of problems that you need to think about, all right? So you don't ground something, what happens to your capacitor? A lot of times, when you do design circuits and something does not work, how do you find out what does not work so you can fix it? It's a problem, all right? It's the most difficult problem. So you have done a circuit, you go and measure it, nothing. Don't find what, find something else. So how are you going to go back and think of what is not working? All right, so you start measuring voltages at different planes. You say, do I have this voltage square? Would I have this one? When you come here and you don't see zero, then you start suspecting, all right, that this is not working. Your capacitors do not work. So these are the kinds of things. And this is the type of thinking that we really need to have. All right, since we have a few more seconds, let's try now to solve the first problem, this one, okay? Since this problem is the one which is grounded. And because it's grounded, this center conductor could have whatever charge you wish. Because either you have a flow of electrons from the ground up, or you have a flow of extra electrons from your conductor down, all right? Whatever is connected to the ground, you have no problem in creating capacitors with that, all right? Because you can, a ground can support whatever charge. Either it can sweep all the negative charge you have, or it can neutralize and then supplement more negative charges, neutralize all of the positive charges that you have by sending electrons and then sending even more electrons, because practically the ground is like a magnet, it's like a magnet. All right, either it absorbs all the electrons, or it can give you a supplement. All right, it's a source and it's a sink. You think of the ground as a source for electrons and as a sink to works the both ways. Okay. So since now we know that these charges are the same, I go to the first one and write C1 equals Q1 over VD. All right. And I know already how much is this. I have found the formula for this parallel plate capacitor. I have found that the formula here, I have found it from before. And therefore, by using this formula, I can find, of course, C1. And then from C1, because you see the formula on the right-hand side does not have any Q1 there. It's only dielectric, area, and H. And I can use this because I've given everything like that, and I can find the capacitance. However, I know that the capacitance is Q1 over VD, and I have VD. So now I can go and find Q1. All right, so I can find Q1 to be so many picocoulombs. And that's the charge on in conductor 1. Okay. Now, in this case, of course, because of the different epsilon, we're going to have different charges. The same charges that I showed you will be what I had in the first case for the charges being identical, assuming that there was air here and air, all right? But because now we have air and dielectric, I go to the second capacitor, which is below, and I'm using now the value for, I'm using the formula to find the value for the capacitance in the second capacitor. The second capacitor is underneath it here. So I'm using and I'm finding the capacitance of that. And then I'm using this formula and I find the Q. Now, in this particular case, Q1 and Q2 can be different. And why is that? Because obviously I can have a Q1 and Q3 that are different, both positive, and I can have here a total negative charge, which is Q1 plus Q3. All right. So the second conductor is going to have as a total charge the sum of these two. The first conductor is going to have Q1. The third conductor is going to have Q3. We found those. And the intermediate conductor is going to have the sum of the two, and it will be negative. And that's this. So practically, to find the first, to just respond to the first question of the problem, it's nothing else that you have to do but remember the parallel plate capacitor, that, and also being able to understand that this is what is going to happen here, and there is no problem with this because of the ground. All right, you have the ability to have as much negative here as you wish if there are two positive. The only thing, if I find this charge and this charge and this charge, then I have to use the formulas that we have given before. You don't, therefore, in this particular problem, you don't use any equations to derive anything. You just use what we have already computed and derived, and you use them as an application for the particular problem. All right. So the second question here that I asked, it says now, all right, if I have these two capacitors and I design them, and they call the MOS capacitors. Why they call that is metal oxide silicon, MOS. That's how they make those capacitors in microelectronics. Okay, so it's a metal. In between is an oxide because it does not have losses. And then usually you have another metal, and underneath it you have silicon. These are called the MOS capacitors, very, very popular. You have them everywhere. Okay, now I want to find the capacitance of these two because obviously this is, I have two voltages, or it could be the same. It could be one source connected to these two conductors and then the ground to this one. Does not have to be two different sources, right? Does not have to be two different batteries. And then says find the total capacitance. If I have one source, for example, connected to this, I'm gonna find the capacitance between A and B, or B and C, or A and C, depending on what I'm trying to measure, right? I can put my probes in different locations and I will try to know what I'm measuring. So in that case, we are gonna do this next time. We're gonna do this problem. But again, look at this ahead of time and feel comfortable about how the charges distribute. That's the step one. If you don't know how to do that, then the other steps, which are easy, will not be able to be accomplished. All right, so we're gonna do this problem next time on Friday. Okay, thank you.
So even when I was in class, it didn't let me answer the topic.
Okay, you're gonna answer it right now.